Hello guys, I am Varun and today I'll be covering the topic interconversion between PDA and CFG. First of all, I'll just basically give you an introduction of what I will cover in this video. So, what is equivalence of CFG and PDA? So, a language is context free if and only if some corresponding push-down automata exists for that language. So there will be two parts, two topics in this particular video. So first will be we'll convert a given CFG, that is the context-free grammar, into a PDA, and in the second part we'll do the opposite. So what is a CFG? So like we can see in formal language theory, a context-free grammar is a formal grammar in which every production rule is of the form A tends to alpha, where A is a single non-terminal symbol and alpha is a string of terminals or non-terminals. So like you can read the rest of it, but I'll move on. So context-free grammar is a type 2 language. And what is a type 2 language? It comes above, like it includes the type 3 grammar in the hierarchy. And what is type 3 grammar? That's the regular grammar that's accepted by finite automata and other things, like non-deterministic finite automata, finite state machine and all. So it's represented by a tends to alpha comma a, that alpha or a, you can say anything, where alpha belongs to non-terminal or terminal. Like you can see, alpha is belonging to V union D, where V is the non-terminal symbols and T are the terminal symbols. So what are these non-terminal and terminal symbols? I'll show you with an example. Like consider that this is a particular language. This is a CFG, a simple CFG. So what happens if we try to expand it? We can get two possible results. Either we write just A and B, and if we just write A and B, these both are terminal symbols. Why? Because there is no further expansion possible. But now consider that I write S, the first expression, then I can further extend it into more things. Like I can further expand it. So I can either write AB, and then these will be the particular terminals, and the language will become AABB from AB. And I can again do, like I can write S. So in that particular case, I can again expand the language and then just continue like this. So hence the usually we use the capital symbols, like capital alphabets for non-terminals and small alphabets for terminal symbols. So like I have given you a simple example that A tends to A, so this will just expand as this. A tends to AB will expand as A comma B, where B will be something, and then this will just expand as A B B B, where these will expand further, and these are the terminal symbols. So moving on, what is a push down automata? So like a push down automata is just simply a finite automaton. What is a finite automata? The thing, like the automata or automaton which accepts the regular language, the type 3 language, that is. So a finite automata plus some memory is called a push down automata. So like we know that we cannot accept uh, strings or languages that require memory in a finite automata, but we can do so in a push down automata. And it's represented by 7 tuple. As you can see, there are 7 elements in the tuple, where q is the set of the states, this sigma is the set of input symbols, this is the set of transition symbol, this is the transition symbol. And how this works is basically, for this one is this is the current state, this particular one is the current state. Then we will write the input symbol here, this will be the input symbol. Then this will be the top of the stack, like there's a memory and we use stack. So what's a stack? It's just a simple data structure. We will just push the items or pop the items. So while pushing, like if we push z not a, this will be like this, and if we pop them, the output will be a z not. It will pop in the other order, so it follows LIFO, last in first out. Since this was the last in, it will go out first. So yes, where were we? Yes, so this was the input symbol, and this will be the top of the stack, and then it will transit to the next state, and this will be the transition or the element that you pushed into the stack. So this is the pushed element. So if I make a particular state of this, so this will be like this for simple starters, then it will become like this, and this will be the new state. The stack will update in this particular case. So next up is the Q0, that is the initial state. Like you know that every automata has an initial state. Then Z is the initial push down symbol. Like I showed you that the stack will consider a Z0. I'll tell you about this later. So this is the initial push down symbol. Then F is the final state, and tau is the set of push down symbols. Like this can be pushed up from the stack. So like I said, the push down automata is more powerful than the finite state machine or finite automata in simple terms. Also, we can divide the PDA into two parts like we did for the finite state machine or finite automata. First is the deterministic and second is the non-deterministic PDA. In this case, the difference is the outputs that we can get. We can get into q into tau raised to a star outputs for this, and in this particular case we raise it to the power of 2. Also, just for knowledge, that the NDPDA is greater than DPDA in terms of expressive power. For the finite automata, it was similar. The non-deterministic finite automata was similar to the power of deterministic finite automata, but in this case, NDPDA is more in power than the DPDA. So, like I said, we'll just start with an empty stack, and we'll consider this particular thing as an empty stack instead of a completely empty stack, since this will help us recognize languages further in the video. Like I have mentioned, Z0 means the stack is empty. So what is the basic working? Like there will be symbols here, and they will be passed into the finite control, and then it will decide whether to push or pop the symbol. Like if we are going to pass this particular string, so I can just say that these are pushed in the, like these are in the input tape, then A will go first and it will be pushed onto the stack, then another A will be pushed onto the stack, then whenever a B comes, the an A will be rejected, and then the second A will be rejected, popped. And like this is the overview of the state transition diagram. What's the state transition diagram is simple. Like we define a PDA using this. We'll make one later in the video. So as you can see, this is the input symbol, this is the stack symbol or top symbol. This represents the element that is at the top of the stack at the moment, and this is the push symbol, the element that will be pushed. So we can also represent this as A comma B, AC, AB. So what this means that when we get the input as A and the top of the stack is B, so let me make the stack. So this is the top of the stack right now. So whenever we get such kind of an input, we get A and the top of the stack is B, it will be updated to AB. Like we'll push A for this particular case. Okay. And how to pop a symbol? Like consider that I have this and then we have A, and now if we are getting a B, like consider instead of this we have a B and we reach A and we want to pop this A. So what will we write? We'll write an epsilon. This is for popping an element from the stack. So it will be popped, and then the stack will become a simple empty stack. So next up we'll move on to how to convert a CFG into a PDA. That's part 1 of the video. So as we'll consider the string, or you can say the grammar, as a raised to n, b raised to n, and c raised to power m, where n comma m is greater than equal to 1. As you can see that a and b have dependency on each other, like the number of a's will be equal to the number of b's in this particular automata, and c is completely independent. So since c is completely independent, we don't need to include it in the stack, so we'll not perform any push or pop operations for c, but we'll do so for a and b. So we'll consider the language for this particular example: A, B, 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 C, C. So how will this be passed? It's passed from left to right always. So how will this work in terms of a stack? The language was A, B, 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 C, C. I'm in the string. So first of all, we'll push the A in the stack, like the empty stack. The initial stack was this with the single Z naught. Then we'll just push into it. Then since we pushed A into it, then we get another A moving from left to right. Then push this onto the stack as well. Then another A, we'll push this particular one onto the stack as well. And then whenever we get a B, we'll pop the corresponding A. So since we got a B, we popped one A. So that leaves us with 2. Then we get another B, we'll pop another A. That leaves us with 1. And then we'll get another B and we'll pop the final A. So that leaves us with the initial symbol. And what this initial symbol will tell us that we now have to pass C. So this is independent of A and B, so we'll not push or pop anything onto the stack while passing C. Hence the output will be A, B, and this will be accepted by the PDA since it was successfully passed. So we can say that any CFG, for any CFG, we can make a particular PDA for the same, as it was visible by this. So now for making this, like I said, we pass this particular string. So first of all, we start with the initial state. So what we are doing is we are pushing it. So for pushing, I told you that if we are pushing something onto a stack, then it will work something like, if this was the initial one that we are considering, then suppose A comes, then Z0, then we'll just update it with AZ0. That means the stack is updated as this. So we are going to write this particular transition here. Similarly, if we get an A and there's already an A on the stack, we'll just push another A. So this covers that. Now when we have passed all the A's, like we passed 3 A's suppose, then we'll get a B, and for the corresponding B we have to pop the particular A. So for popping, I told you we'll just write it like this, or push, and we use a different color. This is pop. So for this we just simply write, and we get an input symbol A, and there's an like consider input symbol B, and there's an A on the top of the stack. We'll just pop it. So we'll just do that here. This is the Q1 state. So we just popped one A. So this eliminates one A and one B. So we'll just continue this unless the till the stack is empty. So we get another B, another A, another B, another A. So now that the stack is empty, we can move on, and we'll just simply push the C. Now how to do that? We'll just pass the C. That means, so we get C and the top of the stack will be Z0. That was the initial one. So we'll not push or pop anything. We'll just keep the state as it is, and this is the final state. We'll just keep on parsing the C, and hence if the language is successfully parsed or accepted by the PDA, it will be a CFG. Like I showed you in depth, like I marked various things, like this was the input symbol and this was the stack top. So this is the updated stack top, like that's the same thing as the other thing, and this implies the pop. I just mentioned it in one diagram, and you might be asking what's this. So we usually call this the acceptance condition. Like after everything has been passed, it will be accepted. So this was converting a CFG to a PDA. Now we'll do the opposite. That was part 2 of the video. So just give me a second. Yes, so the part 2 is PDA to CFG. So for this we'll use the language a raised to power m plus n, b raised to power m, c raised to power n. where m comma n is greater than equal to 1. So this is the corresponding PDA. I have already drawn this. This is the corresponding PDA for the CFG that's given above. So what are the steps involved in this? First of all, we have to make sure that the PDA contains only one final state. As we can see, there's only one final state. So first condition is met. And then the second is that the PDA should empty stack before accepting, pushing the Z0 state at the beginning. So like they are just saying that we have to just push Z0 at the beginning, and we are just considering that as the initial state. So we won't mention this explicitly. So this one is covered at the same time. And now we have to check that there's only one transition at a time. That means there's only either pushing or popping at a particular transition. We cannot perform both the operations simultaneously. We just have to make sure that this is not happening. So I can see that we are just pushing here, we are popping in this particular transition, we are popping here, we're popping here, we're popping here, and we are just like, this is the acceptance criteria, acceptance state or transition. So we can see that all of the conditions are met, so hence our PDA is already minimized or optimized. But there are still two conditions that we have to check. Yeah, this is the same thing, that we always start with this thing and we always end on this thing. So we also have to make sure of that. So there are two problems, underflow and overflow. So what's underflow? Like we can consider that we already have a full stack if the capacity is 3, as is mentioned here. So if we just pop an element, A will be popped, then we pop another element, this A will be popped, and then if we pop this, the final Z0 will be popped. That was our initial stack. Now that we know that the stack is empty, if we try to pop again, it will throw an error called that there's no element in the stack, and this particular condition is called underflow. And what's overflow? It's the opposite. Like we consider that we have a capacity of 3, so the initial stack is less, like I told you. Then you're pushing an A, so the count was 1, 2. Now if we push B, then the count is 3. Now if we try to push A, the count is already full, like we cannot push another element, so this will be called overflow. So to simply now to convert the PDA into a CFG, like first we have to minimize the PDA that we checked above. This particular PDA is minimized, and this was the initial stack. Now we'll define the transition states. Like I told at the starting of the video, we'll just follow that convention. Like we can see that there are two transitions on Q0. So we are getting input A, and the top of the stack is Z0. So we are just updating it with AZ0. So you can see that that one is covered. Then the next one is we are getting input A, the top of the stack is A, and we are updating it with AA. So as you can see, that one is covered as well. Next up, we are popping A whenever a B comes. So we are popping A whenever a B comes, covered. Then we are just going to pop A until the B's are over. So that particular one is covered too. Then similar with the C, we are popping it. And then the final is the acceptance criteria or state. So as you can see, all of these are covered. So based on these transitions here, we'll estimate the language. So as you know that we are just continuously pushing the A's for the first two transitions. So you can safely say that A is pushed n times. You can consider that there will be n A's, like A raised to n in the particular language. So whenever we are encountering a B, we are popping an A. But notice that it doesn't stop there, and we also pop A whenever we encounter C. So that means that the number of B's is not equal to the number of A, that that we are not popping n A's. So we can say that we can just assign a variable Q for this. So we are popping Q A's. A is popped Q times for the number of B's, hence the occurrence of B's will be P raised to Q. And now similarly, we are popping A whenever we are encountering C. Hence it seems to assume that A is popped n minus Q times. Why is that? Since the total number of A's was n, and we are popping A Q times whenever B occurs, so that leaves us with n minus Q. So refactoring the equation, we can safely say that A raised to n plus m is B raised to m and C raised to m, where the total number of B's and C's is equal to the number of a's in the language, where n comma m is greater than equal to 1. So what was our original grammar? As you can see, this is the right answer. So that's how we check the opposite, and hence you can say the first thing that we say in said in the equivalence, that given a PDA, we can construct a CFG that accepts all the string accepted by the PDA. Hence, we have proved these two properties, and that's how you convert, and that's the interconversions between PDA and CFG. Thank you for watching. Hope you enjoy your day.